Hey everyone, and welcome back. We're going to be diving deep today into something that might sound a little, well, technical at first,
hmm
redox reactions.
Yeah.
But trust me, this is way more exciting than just,
Yeah.
equations on a chalkboard.
Absolutely
We're
right.
talking about the chemistry behind things you encounter literally every single day.
That's right. Redox reactions, they're really the backbone of so much, from burning fuel
Right.
to powering your phone, even how your body processes energy.
Okay, I'm intrigued already.
Yeah.
But before we get too far, let's break down what exactly redox reactions are.
Okay.
I remember learning about, oxidation and reduction back in school,
Mm.
but it always felt, I don't know, a bit abstract.
Yeah.
Can you refresh my memory a little?
Absolutely. So in the simplest terms, oxidation is kind of like adding oxygen to something,
Okay.
and reduction is taking it away.
Okay.
A really good example is, think of a rusty bike.
Right.
That's iron reacting with oxygen in the air, forming iron oxide, which is rust. So that's oxidation happening right there.
Okay.
And the opposite of that, extracting pure metal from an ore, that's reduction.
Interesting.
We're removing oxygen to get to that valuable metal.
So those, like, massive industrial processes, those are basically just giant reduction reactions.
That's exactly what they are.
Wow. But I also remember, I think, learning that the definition of oxidation and reduction goes beyond just oxygen, right?
You're absolutely right. As scientists,
Yep.
dug a little deeper, they realize it all boils down to electron transfer.
Okay.
So really, oxidation is losing electrons, reduction is gaining them.
Okay.
Think of it like a game of hot potato.
Okay.
The electrons are being tossed around.
Mm-hmm.
Whichever element loses that electron is oxidized. Whoever catches it is reduced.
Okay, that analogy actually makes it so much easier to picture.
Good.
So how does, like, this electron transfer, how does that actually work in a reaction? Can you give me an example?
Yeah, absolutely. So let's take the formation of sodium chloride, or, simple table salt as an example.
Right.
So sodium really wants to get rid of an electron.
It does.
It does, yeah. And chlorine is very eager to snag one.
Okay.
So sodium loses its electron, becomes positively charged, which is oxidation.
Hmm.
Chlorine gains the electron, becomes negatively charged, that's reduction.
Okay.
And then they stick together, and that's how we get sodium chloride.
So it's like a perfect match.
Yeah.
One element's trash is another's treasure.
Exactly.
And that simultaneous exchange of electrons, is that what defines a redox reaction?
That's exactly it. And what's really fascinating is this competition for electrons.
Uh-huh.
It's not always a tie,
Right.
Some elements are much more willing to give up those electrons than others.
So some are better givers and some are better takers, basically.
Yeah.
And is that why some metals, like, are more reactive than others?
Precisely. And we can actually see this competition in action with, like, a pretty simple experiment.
Huh.
So imagine you have a zinc strip and you place it in a solution of copper nitrate.
Okay.
So what happens is you actually start to see this reddish layer of copper forming on the zinc strip, and that blue color of the solution starts to fade.
Oh, wow.
Yeah, so what's happening is the zinc is actually handing its electrons over to the copper.
We can actually see that.
We can, yeah. So the zinc is oxidized. It loses those electrons, becomes zinc ions that dissolve into the solution.
Okay.
And meanwhile, those copper ions in the solution, they grab those electrons and they become copper metal, and that's what plates onto that zinc strip.
That's amazing.
Yeah, and because this reaction happens so readily,
Yeah.
it tells us that zinc is a stronger reducing agent than copper.
Okay.
It's more eager to give away those electrons.
So that competition for electrons, that's what's driving the whole reaction.
Absolutely. And it's not just limited to zinc and copper. We can do this with, lots of different combinations of metals and see varying degrees of reaction. In fact, this whole concept of electron competition, it's the basis for things like, galvanization, where we use zinc to protect iron from rusting.
So the zinc is, like, sacrificing itself to protect the iron.
Exactly.
Wow, that's pretty noble. But so far, we've been talking about electrons being fully transferred.
Mm-hmm.
What about reactions where they're shared, like in covalent compounds?
Right.
How do we track that electron movement then?
That is a great question, and that's where oxidation numbers come in.
Right.
It's like a bookkeeping system that helps us track electron shifts, even when they're not fully transferred.
So it's a way to, like, simplify things a little bit,
Mhm.
keep track of who's gaining or losing electrons?
Exactly.
But how do we figure out these oxidation numbers?
Well, there's some handy rules. So elements in their pure state, they have an oxidation number of 0.
Okay.
Simple ions, they have an oxidation number equal to their charge.
Okay.
And then we have guidelines for specific elements, like oxygen, which is usually -2. So we use these rules to assign oxidation numbers to each element in a compound. And here's the key point, okay? If an element's oxidation number increases during a reaction,
Okay.
it's been oxidized.
Okay.
If it decreases, it's been reduced.
Got it.
So it's just a simple way to keep tabs on that electron movement.
Okay, so they're like little flags
Yeah.
that signal whether oxidation or reduction is happening.
Exactly.
That makes a lot more sense.
Good.
But what about when we see, like, fractions in those oxidation numbers?
Yeah.
How can you have half an electron?
That's a great question. It seems strange, right?
Yeah.
But those fractions, they're often just averages.
Okay.
Think of it like a basketball team, right? The team's average score might be 2.5 points.
Right.
But each player only scored whole points.
Right. Of course.
Same with atoms in a compound. They have whole number oxidation states.
Okay.
But the average can sometimes look like a fraction.
So it's just a quirk of the calculation, not actual fractional electrons floating around.
Yeah, exactly.
That's reassuring.
Good.
So now that we kind of have a grasp on how to track this electron movement,
Yeah.
can we talk about the different types of redox reactions? Like, how do scientists even categorize all of this electron shuffling?
Yeah, that's a great question. So there are 4 main types: combination, decomposition, displacement, and disproportionation.
Okay, let's unpack those.
Okay, so combination reactions are pretty straightforward. 2 or more elements combine to form a compound.
Okay.
So think about burning carbon and oxygen to form carbon dioxide.
Right.
That's a classic combination reaction. And it's also a redox reaction because carbon is oxidized, oxygen is reduced.
So it's like a chemical merger.
It is, yeah.
What about decomposition reactions?
Those are the opposite.
Okay.
A compound breaks down into simpler substances.
Okay.
So like using electricity to split water into hydrogen and oxygen gas,
Right.
that's a decomposition reaction and also a redox reaction because that hydrogen, its oxidation number changes.
So it's like a chemical breakup. I'm starting to see a pattern here.
Yeah.
Okay, so what about displacement reactions then?
Okay, so these involve one element kicking another out of a compound,
Okay.
like a game of chemical musical chairs.
Right.
And we saw this earlier with the zinc displacing the copper, right?
Yeah.
Zinc stole copper's spot, leaving the copper to fend for itself.
So it's all about who's more reactive, who wants those electrons more desperately.
Exactly.
Okay, so what's that fourth type of reaction?
Okay, that is disproportionation, and it's a bit of a wild card.
Oh, boy.
In this case, the same element gets both oxidized and reduced.
So it's playing both sides of the field.
Exactly.
Wow, that's a real identity crisis for an element.
It is.
Can you give me an example?
Sure. So think of hydrogen peroxide.
Okay.
That's stuff you use to clean cuts.
Yeah.
When it decomposes, it forms water and oxygen gas.
Right.
So the oxygen in the hydrogen peroxide starts with an oxidation number of -1, and then it gets reduced to -2 in the water and oxidized to 0 in the oxygen gas.
Wow, so it's both gaining and losing electrons in the same reaction.
Yeah,
That's pretty impressive.
it is.
It seems like redox reactions are happening, everywhere we look.
They really are, and understanding how they work opens up this whole world of possibilities.
Right.
From harnessing energy to developing new technologies.
I can't wait to delve deeper into some of those applications.
Yeah, me too. Yeah, it really is remarkable how these, tiny little electron transfers are behind so much of what we see and experience in the world around us.
I know. It's like we've uncovered this hidden language of chemistry, kind of, that's operating all around us. It's pretty amazing.
It is.
But before we, get too philosophical,
Right.
I'm kind of curious about something you mentioned earlier, those standard electrode potentials.
Okay.
How do those help us, predict whether a redox reaction will actually happen spontaneously?
That's a great question. It's all about comparing those potentials.
Okay. So imagine we have two, contenders in our electron competition, right?
Okay.
Let's just call them A and B.
So,
Each one has an oxidized form, so A plus and B plus, and a reduced form, A and B.
okay, so A and B are like our electron hot potato players, and they can either have the potato or not have the potato.
Exactly. And the standard electrode potential, it tells us how much each contender wants to hold on to that electron.
Okay.
So if A has a more negative standard electrode potential than B, it means A is more eager to toss that electron away.
Okay.
It's a stronger reducing agent.
So A is more likely to force that electron onto B, making B reduced.
Precisely. So that means the reaction where A reduces B plus would happen spontaneously.
Okay.
It's kind of like a ball rolling downhill.
Right.
It naturally wants to go from a higher energy state to a lower one.
So by looking at those standard electrode potentials, we can predict which way the electron's going to flow and which reactions are actually likely to occur.
We can. Yeah, it's like having a crystal ball for chemistry.
It is. That's amazing. It gives us a really powerful tool to predict how different substances are going to interact.
Yeah.
Of course, there's other factors too, like temperature and concentration that could play a role, but
Right.
standard electrode potentials are a great starting point to really understand what's driving these reactions.
This is all connecting so well, like back to those electro processes that we were talking about earlier.
Yeah.
It's like those two worlds, the chemistry and the electricity, they're just like inseparable.
They are, yeah. And to understand that connection even better, let's dive a little deeper into what's actually happening at those electrodes.
Okay.
So remember, in a redox reaction,
Yeah.
we have both oxidation and reduction occurring, right?
Right.
But in an electrochemical cell, we actually separate those processes.
So we're giving each half of the reaction its own stage to perform on?
Exactly. So the electrode where oxidation happens, that's called the anode.
Yeah.
And the electrode where reduction happens is called the cathode. And these two electrodes are connected by an external circuit, allowing those electrons to flow between them.
So it's like creating a pathway
Yeah,
for the electrons to travel from the element that wants to lose them to the element that wants to gain them.
that's a great way to put it.
Cool.
And to complete that circuit and to keep the reaction going,
Yeah.
we use a salt bridge,
Okay.
and that allows ions to flow between the two solutions and keep everything balanced.
So it's like a chemical bridge
Yeah,
that makes sure that the charges stay neutral in both solutions.
precisely. And it's this flow of both electrons through the wire and ions through that salt bridge that keeps the whole system running.
Okay, cool.
But let's zoom in even closer, okay?
Okay.
Let's look at what's happening at the molecular level at each electrode.
All right. So I'm picturing those tiny atoms and electrons just doing their dance.
Exactly. So at the anode,
Okay.
let's say it's made of zinc, okay?
Okay.
Zinc atoms lose electrons, they become zinc ions,
Yeah.
which then go into the solution. And those lost electrons, they kind of hang out on the surface of the electrode, giving it a negative charge.
So the anode becomes negatively charged because it's accumulating all those electrons from the oxidation process.
Exactly. Now, at the cathode, let's say it's copper.
Okay.
Copper ions from the solution
Yeah.
are grabbing those electrons that traveled through the wire,
Okay.
and they're turning into copper atoms, which then deposit onto the electrode.
So it's like those copper ions are getting reunited with their lost electrons thanks to that external circuit.
Exactly. And this process uses up electrons at the cathode,
Okay.
giving it a positive charge.
Ah, so the anode is negative because it has too many electrons, and the cathode's positive because it's constantly using them up.
Right.
It's like this constant push and pull between the two.
It is, yeah. And it's this difference in charge between the anode and the cathode
Uh-huh.
that creates that potential difference, or voltage,
Okay.
which drives that flow of electrons through that external circuit.
So we're essentially harnessing this chemical tug of war to generate electricity.
We are.
This is how batteries work. Yeah.
Exactly. Batteries are essentially electrochemical cells
Okay.
that store chemical energy and then release it as electrical energy.
Okay.
And the same principle applies to fuel cells.
Right.
But instead of having like a limited amount of reactants like a battery does,
Yeah.
fuel cells are continuously supplied with fuel and oxidant from an external source.
So it's like a battery that never runs out.
That's the idea.
Wow.
And a common type is the hydrogen fuel cell,
Right.
where hydrogen gas is the fuel
Okay.
and oxygen from the air is the oxidant.
I've heard a lot about hydrogen fuel cells, as a potential clean energy solution.
Mhm.
What makes them so special?
Well, they're incredibly efficient at converting chemical energy into electrical energy, and the only byproduct is water.
That's amazing.
But there's still some challenges,
Of course.
like finding safe and efficient ways to store and transport that hydrogen gas.
All right, so there's always a catch.
Always a catch. Yeah.
But the potential benefits are, really exciting.
They are, yeah. And it all boils down to harnessing the power of redox reactions
Right.
to create a more sustainable future.
It's amazing to think that something as fundamental as electron transfer
Yep.
could hold the key to solving some of our biggest energy challenges.
It really is. And we've only just scratched the surface.
Yeah.
As we continue to explore this world of redox, I think we're bound to discover even more innovative applications.
This has been an incredible journey so far.
Yeah.
I'm already eager to see where else these redox reactions take us.
Mm-hmm.
But before we wrap up,
Yeah.
you mentioned earlier that our bodies are essentially like complex electrochemical systems, right?
They are.
Can you elaborate on that a little bit?
Yeah, absolutely. So think about respiration.
Oh,
The process by which we get energy from food.
right.
It's a series of redox reactions where glucose, a type of sugar, is oxidized and oxygen is reduced. And that produces energy for our cells.
So the oxygen we breathe is like the final electron acceptor in this whole cellular energy production process.
Exactly.
Wow, it's like our bodies are running on redox reactions.
They are. And it's not just respiration.
Right.
Other vital processes like photosynthesis in plants, the transmission of nerve impulses,
Wow.
even the way our bodies fight off infections, all involve redox reactions.
That's mind-blowing to think that something, as tiny as electron transfer
Yeah.
is at the heart of such like complex and essential life processes.
I know. It's incredible.
It really highlights how fundamental redox reactions are to our understanding of not just the world around us, but like
Yeah.
the intricate workings of life itself. It's amazing.
Yeah, it really is.
This deep dive has truly expanded my horizons. I feel like I've gained a whole new appreciation for the power and just the pervasiveness of these redox reactions,
I'm glad to hear that.
Yeah, it's really amazing.
The next time you strike a match, start your car. Even just take a breath.
Yeah.
Remember those tiny electron transfers that are making it all possible.
Thanks for joining us on this incredible journey into the world of redox. Until next time, stay curious and keep exploring. It's incredible to think that those tiny electron transfers are happening inside us all the time,
I know, right?
keeping us alive and functioning.
It's amazing.
It is, but we've been talking a lot about, like the theoretical side of redox reactions.
Mm-hmm.
Can we shift gears a little bit and explore some, like, real-world applications?
Yeah, absolutely.
What are some specific examples of how we actually use redox reactions in different fields?
Oh, the applications are practically endless.
I bet.
They're the workhorses behind so many industries and technologies. It's really incredible.
Yeah.
Let's start with something we all rely on. Energy production.
Okay, back to combustion.
Yeah.
We talked about, like, burning fuels,
Yeah.
wood, coal, natural gas, all that.
Right.
How exactly does that fit into this whole redox picture?
So basically, when we burn those fuels, we're oxidizing the carbon and hydrogen in them,
Okay.
combining them with oxygen from the air,
Right.
and that releases energy in the form of heat and light, which we can then use to power our homes and industries.
So those, like, cozy fireplaces and powerful engines, those are essentially just giant controlled redox reactions.
That's exactly what they are.
Wow. That's pretty amazing.
It is, yeah. And the same principle applies to the internal combustion engines in our cars.
Right.
We're combusting gasoline or diesel,
Uh-huh.
and the energy released from that redox reaction, that's what powers the vehicle.
So every time I fill up my gas tank, I'm basically providing fuel for a series of mini explosions
Yeah.
driven by redox reactions.
Mini explosions driven by redox, that's a great way to put it.
I never thought about it that way.
It's pretty cool when you think about it that way, yeah.
Yeah, it is. What other applications are there?
Well, redox reactions are also crucial in metallurgy,
That's
the science of extracting and processing metals.
Right.
Remember how we were talking about extracting pure metals from their ores?
Yeah.
That involves reduction.
Yeah.
We use reducing agents to remove oxygen from those metal oxides, leaving us with that pure metal.
So those, like, massive industrial processes that turn those raw ores into the shiny, usable metals we all use, those are just large-scale reduction reactions.
They are.
That's pretty impressive.
It is, and redox reactions, they aren't just used for extraction.
Okay.
They're also key for refining metals. Removing impurities, enhancing their properties, making them stronger, more durable,
Right.
resistant to corrosion.
So redox is involved in pretty much every step of the process, from digging up the ore to creating the final product that we all use.
It really is, yeah. And beyond energy and metallurgy,
Yeah.
redox reactions are also essential in chemical manufacturing.
Okay.
For instance, they're used to produce caustic soda.
What's that?
That's sodium hydroxide.
Okay.
It's used in everything, from soap making to paper production to water treatment.
Wow, so even those everyday products we all take for granted
Yeah.
rely on these redox reactions kind of happening behind the scenes.
They do.
It seems like redox is truly everywhere we look.
It is, and it's not just about creating things, right?
Yeah.
Redox reactions are also crucial for understanding and addressing environmental issues.
Okay, now that's interesting.
Yeah.
I wouldn't have immediately connected redox reactions with the environment.
Right.
How do they play a role there?
Well, think about the hydrogen economy that we were talking about earlier.
Uh-huh.
The whole idea is to use hydrogen gas as a clean fuel,
Right.
producing only water as a byproduct.
Right.
And that process of converting hydrogen and oxygen into energy in a fuel cell, that's a redox reaction.
Right. So understanding and harnessing those redox reactions
Yeah,
could be a key to developing more sustainable energy solutions for the future.
absolutely. And on a, less positive note,
Okay.
the formation of the ozone hole, that's a major environmental problem, right? That's also linked to redox reaction.
Oh, wow. I remember learning about how certain chemicals like CFCs
Mm-hmm.
were depleting the ozone layer.
Right.
How does that relate to redox?
So those CFCs, they were widely used in refrigerants and aerosols,
Right.
and they can break down in the upper atmosphere,
Uh-huh.
releasing chlorine atoms.
Okay.
And those chlorine atoms then catalyze the destruction of ozone
Oh, wow.
through a series of redox reactions.
So understanding these redox reactions is crucial, not only for, creating new technologies and products, but also for understanding
Yeah,
and mitigating the negative impacts that we have on the environment.
exactly. Redox reactions are truly fundamental to so many aspects of our world.
Yeah.
And the more we understand them,
Yeah.
the better equipped we are to both harness their power
Yeah.
and address the potential consequences.
This has been such an eye-opening deep dive. I feel like I've gained a whole new appreciation for the power and the pervasiveness of these redox reactions.
I'm glad to hear that.
Yeah, they're amazing.
They are.
Well, thank you so much for joining us on this incredible journey into the world of redox.
Yeah, it's been my pleasure.
Until next time, stay curious and keep exploring.